All right, so we're going to revisit writing and evaluating exponential functions. This time we're just looking at from a table with an emphasis on Desmos. So we're going to go ahead and label this. We're going to be using Desmos today since we've done it by hand, but I am going to recap how to do it by hand as well. Okay, so I'm going to let you do this first question, but I'll give you an example before you do it. So I'm going to start right here. At the beginning of April, a colony of ants has a population of 5,000. Okay, so what does 5,000 mean? All right, so let's start again with the exponential function so we can see what it is. If you forgot the formula, it is on the formula sheet. So you're looking for exponential equations, and here it is at the bottom left, y equals abx. You are responsible for knowing what y equals abx means. So let me just remind you once again. Okay, what does a mean? A is my y-intercept if what? If there's no number right here, right? If there is a number right there, remember your y-intercept is a plus that number. Okay, but for now we're going to be having a y-intercept of 0 because there's nothing there, which means math means 0. All right, so that's my y-intercept. And then what does b represent? So we have two options for b. We have growth. And what does that mean? It's going up, increasing. This has to be greater than 1 for it to be increasing. And then we also have decay. And what does that mean? It's decreasing, right? And for it to be decreasing, it has to be between 0 and 1. So B is between 0 and 1. So just a quick recap as to what we did in the previous videos, just to make sure we can still answer these questions. But however, we are going to be mostly focusing on our calculator, but we are going to do it by hand anyway. All right, so scientists noticed that the company population was decreasing each month by 80% of the previous month's population. Okay, so looking at question number 6, is the ant population an example of exponential growth or decay, and explain? Okay, so I just need to know, is my B growth greater than 1 or decay between 0 and 1? Well, how do I calculate B? Well, we can look at the table because they give us a table. What do you notice about the numbers? They're decreasing, right? So if I know for sure that this is an exponential function, then I can say this is decay. But I don't know for sure that's an exponential function until I find that b is the same each time. So how do I find what b is? Remember, you take the second one and divide it by the first one. You can also do the third divided by the second, or the fourth divided by the third, basically the one before it. You cannot do like the fourth divided by the first. That's going to be wrong. So it has to be sequential in order. The second, which is 4,000, and remember, it has to be the second first. The order does matter. So the second one, which is 4,000, divided by the first one, which is 5,000. You're going to put that in the calculator. That's going to be 4/5, which is going to be 0.8. Or you can leave it as a fraction. So I'm going to put it as a decimal because it's easier for you guys to see whether it's greater than 1, less than 1, or in between. All right, so again, I'm just going to put this in the calculator to show you. So 4,000 divided by 5,000. You see, it's 0.8, or as a fraction, these zeros cancel to leave 4/5. But either way is fine, as long as you know, right, that why is it exponential first? Well, let's check. So from here to here is 0.8, but I don't know this is an exponential function until I prove that every single time the change is 0.8. So I'm going to start at 4,000. And if I multiply it by 0.8, it should give me the next number. Does it give me the next number? It does, 3,200. So multiplying by 0.8 gives me the next one. And if I multiply it again by 0.8, and does it give me the next number, 2560? It does. So this is an exponential function. Why? Because it is changing by the same factor or the same rate, okay? So multiplying by 0.8 every time means it's exponential. Therefore, I can say now it's exponential decay. I couldn't say it was decay before because I didn't know if it was exponential or not. So this is decay. And now what's the reason as to why it's decay? So looking back at your notes, okay, it's decay if it's between 0 and 1. It's growth if it's greater than 1. If you look at 0.8, it's between 0 and 1, therefore it is decay. So when you have to explain it, you're going to say 0.8 is between 0 and 1. That makes it decay. If I'd gotten 3, for example, that would be growth. Why? Because it is greater than 1. Whenever you're multiplying by 0.8, it's going to be going down. It's going to be decreasing. All right, so what is the equation that models the ant colony population A? Now be very careful because anytime they give you letters, you have to use their letters. M months after it was first measured. All right, so I have to use A and M. So the total population is A. So A is equal to, all right, what is my start? So remember, my start happens at x equals 0, and we're going to make a note of it again because we're just going to write it every single time. X equals 0 is my y-intercept. That way you don't get confused, which is my start. All right, by the time we finish all these videos, you should really know this inside and out. All right, so my start is where x equals 0, which is what? 5,000. So this is 5,000. My b, how am I growing each time? So 0 multiplying by 0.8. And then my time, did they tell me what to use? So I'm going to use x. All right, so that's my equation for my exponential decay. What is an appropriate domain and range? So let's remember what domain is. So domain is x left to right. All right, so let's start at the left. Okay, so think about, and as a matter of fact, since I've got my equation, I'm going to go ahead and put it in so you guys can visualize what I'm about to say. So I'm going to put 5,000 parentheses 0.8 close parentheses shift. So it can go to the top x. All right, so that's my function. I'm going to zoom out, or yep, there's my function. All right, so left to right. Where does this start? Now, it has to be in context of what we're starting with, right? What's the furthest to the left? Does it have anything less than 0? Can I have negative 1 month? No, so my start is 0. All right, so I'm going to start at 0 is my left, comma, my right-hand side. Okay, my right-hand side is, where does it stop? So here's a line, there's a line, there's a line. Let me change this color so that you can distinguish it. There's a line, there's a line, there's a line. Technically, it goes on forever. But if you zoom in, so this is 396 months, all right, it's not quite going to quite be 0. And maybe it's easier for me to show you in the table. Let me show you in the table real quick. And this was 396 months. So this number in scientific form is so small that it looks like it's very close to 0. And that's what it's trying to say. So technically, I guess it never stops. We're going to say infinity. But honestly, as this is a real world, you know, I don't know if I'd really agree with infinity, but hey, it gets very, very close. All right, so this is going to be open because it's infinity. What about the 0, where I started? When I started at 0 months, was there some number or was it a whole? There was a number there, so this is going to be closed. All right, so now we're going to go to range. And what was the range again? The y. And that's going to be from the bottom to the top. All right, so let's start with the bottom. What was the bottom of this graph? Let me hit home. All right, so zoom out a little bit. There's the bottom. All right, where's the bottom? This is an isotope, which means it doesn't touch 0. So the bottom is 0. But because I just said it doesn't touch it, I leave it open. And then where is the top? So technically, even though, let me make this completely big actually. Even though you're going to see it, let me go to 5,000. 2,000, 4,000, 5,000. All right, I'm going to zoom in right here. All right, boom. You see at 5,000? We've passed 5,000. You can see it's going to the negative side, right? On the top, right? So, but here's the thing. Because we know our ant population started at 5,000, we can't go to any number above 5,000. So when I go look at 5,000, 558... 7. Give me just 1 second. Let me get there. All right, 51 there, 50. Boom. At 5,000, it's 0 months. Anything after 5,000, look, I'm in the negative number of months. And can you have that in a real world situation? Absolutely not. So the top of my graph cannot go past 5,000. And why can it not go past 5,000? Because we can't have negative months. Do I include 5,000? Is there a point at 5,000? Yes, there is, so I close it. Okay, so we're going to practice a lot of these just so that you can get real comfortable with looking at that in real world. All right, question number 9, complete the following statements. As the month increase, the ant colony population does what? So as the months are going up, what's happening to the population? They are decreasing. So I'm just going to write decreasing or as an arrow down. Number 10, estimate the ant colony population on month 1.5. Show your work. Okay, so month 1.5. So here's my equation right here. And they're saying that the time is 1.5. So all I got to do is just write out the equation. So 5,000, 0.8, and then 1.5 is the time. Now, two ways you can do this. You can type that in here, but I already know this is here. Did I make a table? I did. And since I've already made a table, I can just say 1.5. And I totally forgot I was supposed to be doing this by the Desmos calculator. So I'm going to quickly show you that, how to do that as well. So 1.5 is my time. And now this is a real world problem. So can I have 0.7 of, what is this, ants? Can I have 0.7 of an ant? No. So, but I can't round it up to 8 because it's not, this is not a full ant. So the answer is 3,577. So 3,577. All right, and because I totally forgot to do this by Desmos, I'm going to redo the entire question real quick because I was supposed to be doing it with a calculator. All right, but I am going to go through it a little bit fast. If you look on the next page, you'll see your notes, which are right here. These are what you're going to be doing. Input the coordinates into Desmos, hit create table. So I'm going to do that right here. All right, so I do apologize because I was supposed to have done that the whole time. All right, so it says input the coordinates. So how do I input the coordinates? I click table and I put in the coordinates. So I'm going to put 0, 1, 2, 3, and then it goes 5,000, 4,000, 3,000, 3,200, and then 2,560. All right, so I put in the table. Then my next step says type the equation for exponential function. What are the two things you have to change in the calculator for it to recognize that what you are doing? So same as before, you type it in the equation. So y equals a b and then shift 6x. All right, obviously it's saying that there's errors. If you remember, just like we've been doing before, I'm going to copy and paste this real quick because I'm going to need it a little later. There are two things you have to change. For one, you have to tell the calculator, hey, I want you to look at this table. Because you want the calculator to look at this table, you have to use what it says right here. So I'm going to change where I see x to x1, where I see y to y1. So just come right after it and type in the ones. All right, then there's one more thing you have to change because now it's completely disappeared. It doesn't like the equal sign. You have to hit the squiggly line. So you can do shift squiggly line right underneath escape, or you can come here, click ABC, then squiggly line. As soon as you do that, it gives you your start. So now we're going to check our answer, which was 5,000 right here. And then our B, which is 0.8. And then it says, so type the equation type in the equation with the value of A and B that you found in step 2. So here's my A is 5,000 and my B is 0.8. Then it says make the equation a table, click gear, then table. So I can come here and make it a table. That way I can find any value that I want, right? So type any value that you like to find the value of. All right, so now I'm back to my questions. So actually this comes right in time. So if I'd wanted to find 1.5, I just come to X and I can just type here 1.5. And you can see it's 3,577. All right, so that's how you use the calculator. So there are 3 steps. You put in the table, you type in the equation with the 2 things, you write the actual equation and make it a table, okay? All right, so what does 3,2,560 mean in context? All right, so what we're looking at is how do I write this in context? So this is my X, this is my X, and this is my Y, right? So let's look at my table real quick. This is my X, and this is my Y. So just tell me, what does 3 mean in my table? So 3 is X, so I go 3 is X right here. So what is this? Number of what? Months. So 3 is the number of months. 2,560 is the ant colony population. Now just write a sentence. What's happening in this question? The beginning of April, a colony of ants has a population of 5,000. As scientists notice the colony population is decreasing every month. All right, cool. So what does this mean in context? That after 3 months, there was 2,560 ants in the colony. Okay, something along that line. So after 3 months, after 3 months, I'm just going to abbreviate, there were 2,560 ants in the colony.